Hello everyone, welcome. What we have been doing is we have been demonstrating the concept of slope deflection method. We have already done so for beam problem. Now today we will demonstrate that through some problems in frames, and the next class also will continue with frame. Now, so today's topic is analysis of frame using displacement method, or more particularly slope deflection method. Now, there are the problems in frame can be broadly divided into two parts. You see, the first one, the first two rather. These frames are called the frames without sidesway. Without sidesway means, okay, before that you see, now compare this is the deflected or the deformation behavior of these two frames, the first and second, vis-a-vis the third and fourth. In third and fourth, what happens that due to the lateral load, there is a sway takes place in a particular direction. Okay, for instance, in this case also. In this case, this is the amount of sway takes place. Okay, this point moves in this direction, this sway takes place. For this case also, these points move in this direction, this amount. Okay, this point moves in this direction by this amount. Whereas in this point, all the joints they can rotate. Okay, rotation can take place. For instance, the rotation of this joint, there is a rotation at this joint, rotation at this joint, rotation at this joint, but all the joints they remain at the position. So, there is no sway in these joints. Okay. So, what we do, these kinds of frame is called the frames without side sway, and these frames are called frame with side sway. So, what we do is we today we'll see one with some example of frames which doesn't have any sway, and in the next class we'll see if there is a sway in the frame, then how it is to be considered in your analysis, and how the amount of the sway to be determined. Okay, so we'll start with these kind of problem today. Okay, now the problem, let's take this problem. It is there is a portal frame which is subjected to uniformly distributed load. Okay, so this is the problem. We will apply the slope deflection method for this problem. Okay, we will go with all the steps that we learned in the previous classes. Now, the first step is, now this frame has three parts. One is part AB, BC and CD. Okay. Now, first is we need to determine the fixed end moments, right. This is the step 1. So, step 1 is fixed end moments. Now, fixed end moments, if you see for part AB, there is no external load applied on in this part. So, fixed end moment in part AB will be 0. So, fixed end moment MF part AB at A, that's equal to MBA fixed end moment at B in segment AB, they are equal to 0. And similarly for CD, you check if you take CD separately and make and there is no suppose what is the primary structure for CD? The primary structure for CD become this. This is C, this is T. So, both ends are fixed. Similarly, for primary structure for AB become this. So, there is no load. So, M at this point and this point, the fixed end moments will be 0. So, this C D fixed end moment is equal to M D C fixed end moment, they all are 0. Okay. Now, what is the primary structure for member BC? Primary structure for member BC become this, and this is uniformly distributed load. This is B, this is C. So, what will be the fixed end moment? We have seen if it is a fixed beam subjected to uniformly distributed load, then the fixed end moments are W or Q L square by 12, right. So, then fixed end moment BC, MBC, MBCF, and the what will be the direction of fixed end moment? Direction for fixed end moment is this. in this case. Okay. So, at B it is anti-clockwise and at C it is clockwise. So, MBC minus MBC is equal to MCB F is equal to QL square by 12. Okay. So, Q is 7.5 into L square is 10 divided by 12, that is 10 meter, and this value is you get 62.5 kilonewton meter. This is minus M B C F is equal to minus C B F. Okay. So, this is the fixed end moment and this is fixed end moment for other members. Okay. So, this means at B C it is minus 62.5, at C B it is 62.5. So, this is step 1. Now, step 2 was apply the slope deflection equation. Now, we need to apply slope deflection equation for AB and BC and CD. Okay. Now, let us see what information do we have. Okay. Now, there is, as I said, there is no sway in any member. So, delta is equal to 0. So, if you recall, the equation for slope deflection is a general equation which has rotation and translation as well, support settlement or sway as well. So, in this case delta is equal to 0. This is the information we have. Then also points support A and support D, they are fixed supports, right. So, theta A is equal to theta D, that should be equal to 0, isn't it. So, only unknown then we have is rotation at B and rotation at C. Okay. So, let us apply the slope deflection equation for span AB. For this is step 2. So, for AB. Okay. Now, what would be the slope deflection equation for AB? That will be MAB will be AB fixed end moment plus 2 EI by LAB 2 theta A plus theta B plus delta, there is no delta is equal to 0. Now, MAB, this gives you, now what we have is, we have this is equal to 0, this is equal to 0 and then theta A is equal to 0, LAB is equal to 5. So, this become 0.4 EI theta B. So, that is MAB. Okay. Similarly, we can do it for BA. MBA will be MBA fixed end moment plus 2 EI by LAB into theta A plus 2 theta B, delta is equal to 0. Then this gives you MBA is equal to, this is fixed end moment, this is again 0 here. So, this is 0, again theta A is equal to 0 and this becomes 0.8 EI theta B. So, this is for BA. Okay. Now, let us do it similar, let us do the similar exercise for other members, member BC and then member BC and member CD. Okay. Now, what is for BC? For BC is, for BC, MBC is equal to M fixed end moment BC plus 2 EI by LBC, then 2 theta B plus theta C. Okay. And this become MBC is equal to fixed end moment is 62 minus 62.5. So, this is minus 62.5 and length of BC is 10. So, this becomes plus 0.2 EI into 2 theta b plus theta c. Okay. This is plus theta c. Okay. Now, so this is, and similarly MCB becomes fixed end moment plus 2 EI by L BC, and this is theta b plus 2 theta c, and this becomes MCB is equal to 62.5, which is the fixed end moment, and then 0.2 EI theta b plus 2 theta c. Okay. So, this is MCB, and then we can do it for CD. Now, again CD rotation at D is equal to 0, and the fixed end moments at C and D both are 0, similar to AB. So, the expression that you get is MCD is equal to 0.8 EI theta c, and then MDC is equal to 0.4. The expression will be very similar to theta c, very similar to AB, which is obvious because the structure, if you look at the structure, this is a symmetric structure, isn't it? So, whatever you get for AB, you get the similar expression for CD. So, we have done the step 2 is now completed. So, slope deflection equations for all these members we have. Next step is to apply the equilibrium conditions at various joints, equilibrium at A, equilibrium at B, equilibrium at C, and equilibrium at D. Okay. Now, step 3 is equilibrium. Let us apply the equilibrium condition. Now, so step 3. Now, we have equilibrium for first at B. You apply equilibrium at B. Equilibrium at B will be MBA. We know that MBA plus MBC, that should be equal to 0. Okay. Now, we have already obtained the expression for MBA and MBC, and if you substitute that, this is 0.8 EI theta b minus 62.5 plus 0.2 EI theta 2 theta b plus theta c, that is equal to 0, and finally, what you get is 1.2 EI theta b. Please check these values, 0.2 EI theta c minus 62.5 is equal to 0. So, this is your equation number 1. Okay. And similarly, we can have at C, and what is the equilibrium condition? MCB plus MCD is equal to 0. That is the equilibrium condition. Similarly, if we substitute the expression for MCD and MCB and MCD, the equation that we have is 0.2 EI theta b plus 1.2 EI theta c plus 62.5, that is equal to 0. So, this is your equation number 2. Okay. Now, if we write this equation in a matrix form, then what we have? We have, you see, if we take EI common, this becomes 1.2 and then 0.2, 0.2 and then 1.2. This is theta b, theta c, and is equal to 62.5 minus 62.5. Okay. Now, again this becomes this is KBB, this is KBC, this is KCB, and this is KCC, and these are all stiffness coefficients, and this is associated displacement, and this is equivalent joint load. Okay. So, this becomes FB and this become FC, and if you write in a 1 to numbering, so this becomes F2, this becomes F3. So, this is the expression that we have seen in a derivation of slope deflection equation and discussion of displacement method as a whole. Now, what we need to do? We need to solve this equation. We need to solve this equation to get the theta b and theta c, and if we do that, the expression that we get is this. The final expression that we get, this is theta b, we get theta b is equal to 62.5 by EI, and theta c is equal to minus 62.5 by EI. Again, which is again expected because it is a symmetric structure. So, theta b, rotation at B and rotation at C will be in opposite direction. The value will be same in opposite direction. So, this was step 3, and final step 4 is, now if we substitute this equation in all these slope deflection equation that we have obtained. For instance, this is the slope deflection equation for AB, and this is for BA, and similarly this is the slope deflection equation for BC, and this is CB. Now, what we have to do is we have to substitute the values of theta B and theta C in this expression to get the corresponding moments, and if we do that, then the corresponding moments will be, I just write the final values. MAB is equal to 25 kilonewton meter, MBA 50 kilonewton meter, MBC 50 minus 50 kilonewton meter, MCB is equal to 50 kilonewton meter, MCD is equal to minus 50 kilonewton meter, and finally MDC is equal to 25 minus 25 kilonewton meter. Now, you see at what is the condition for at joint B? MBA plus MBC is equal to 0, 50 minus 50. What is the equilibrium condition at joint C? MCB plus MCD is equal to 0, 50 minus 50. Okay. Now, let us draw the bending moment diagram. Bending moment diagram is this. Again, as I said, this sign gives you whether the bending moments are positive or negative, whether the bending moments are clockwise or anti-clockwise, but when you draw the bending moment diagram, we need to consider whether the bending moment is sagging or hogging bending moment. For instance, for this is A, B, C, D. In AB, bending moment is 25. 25 means it is clockwise, right? It is clockwise, and for BA it is 50. Again, it is clockwise. It is clockwise. For BC, it is minus 50, means it is anti-clockwise, and for CB it is 50, means it is clockwise, and again for CD it is minus 50 means it is anti-clockwise, and again for DC it is minus 25 means it is anti-clockwise. It is anti-clockwise. It is anti-clockwise. Okay. Now, for MBC and MBA is fine. Okay, fine. So, now what you have to do is this is clockwise and this is clockwise, and this is anti-clockwise, and this becomes clockwise, this is anti, this is like this, this is like this. Okay. Now, this is the bending moment, these are the bending moments. Now, when we draw the bending moment diagram, we need to see whether they are hugging moment or sagging moment, or we draw the bending moment diagram in the, when the bending moments are drawn in the compression side, at least as per our sign convention. Okay. Now, so what would be the bending moment diagram? The bending moment diagram will be something like this. Okay. So, the first is the total bending moment will be the bending moment due to the external load and the bending moment due to the these internal these moments. Okay. Now, your the loading was something like this. So, for external load there is no bending moment in this, there is no bending moment in this. So, for external load bending moment will be only on BC, and we know it is a parabolic bending moment, parabolic bending moment diagram. So, this is positive bending moment. Okay. Now, you see this bending, this is hogging bending moment as per our sign convention. Okay. So, this bending moment will be negative bending moment. So, this value is 50. So, this bending moment will be negative bending moment. Okay. And both this is negative bending moment. Okay. Now, again this is this value is MBA is 50. So, this is, and this is, and then we have a value like this, and similar here and similar here. So, you draw it, you draw it. Now, this becomes the bending moment diagram. Now, what is the bending moment for this? These are the bending moment. These are the, this is the bending moment diagram, and the values are, this is 25, this is 25, and then this is 50, this is 50, this is also 50, this is also 50, and this becomes this total becomes, and this total becomes 93 point, this total becomes 93.75. So, actual moment at this point will be 93.75 sagging, and then minus 50 which is hogging. So, moment at the midspan will be only this part, and this part will be 43.75. So, this is the bending moment diagram. Now, again another way you can draw the bending moment diagram is as per, you first draw it in, when you draw the bending moment diagram. Another way is you always draw the bending moment in the compression side, okay, depending on whether it is a hogging moment or sagging moment. Now, okay, so this is the first example for frame which does not have any sway. So, let us see quickly the second example. The second example is this, which is again. So, quickly let us see what is the example. The example is this, it has 3 member, this is, so this is A, then B, then C, D, and the loads are, this is subjected to 1.5 kilonewton per meter, there is a concentrated load 5 kilonewton, and then there is another load here which is 4 kilonewton, dimensions are given. Okay. Now, the first step, as we know, the first step is to step 1 is to draw the, is to find out the fixed end moments. Now, what is the fixed end of AB? So, the primary structure becomes like this, the AB become this, then BD become this, and then CD becomes, and what are the loads on it? This is 5 kilonewton, this is uniformly distributed load 1.5 kilonewton per meter, and then this is 4 kilonewton. Now, you see, so this is the primary structure subjected to external load. This is again a fixed beam subjected to a concentrated load at the midspan, fixed beam subjected to uniformly distributed load, and again this is a fixed beam subjected to a concentrated load at the midspan. So, we can find out all these, this is A, B, D and then C. So, we can find out what is MAB, MABF and then MBAF. This is the fixed end moments for AB, then MBCF and MCBF. This is the fixed end moment for BC, and then similarly MCDF, CBF, which is fixed end moment at C, and then similarly MBC at F. Okay. So, we know how to determine all these fixed end moments. Okay. Once we have these fixed end moments, now what informations, then step 2, this step 2 was what? Step 2 was writing the slope deflection equation. Now, what information we have, you see here. Now you see slope at delta is equal to 0 anyway, there is no sway in this. Another information we have that theta A is equal to 0 and then theta C is equal to 0. Okay. So, only unknown we have here is theta B. Okay. Now, you can say that that displacement and delta is also unknown. In order to find out the member forces displacement, and without actually computing the displacement at point D, just by knowing the rotation at B, you can compute the member forces. Okay. Now, that is a very important thing, because when you take any structure can have many kinematic indeterminacy. Now, you need to reduce your problem, we need to reduce the computation, right. Now, we need to identify the amount, many kinematic indeterminacy, many degrees of freedom. If you need to identify what are the degrees of freedom, if I know them, then the internal forces can be determined. Okay. Now, you take only those, you compute only those rotations and displacements. This makes your computation slightly or reduce your computation. So, this is theta B. Now, if we apply all these the equilibrium conditions for not slope deflection for AB, BD and BC, and finally, so this is step 2, and then step 3 is applying the equilibrium condition. Now, what equilibrium condition we have here is, equilibrium condition at B is, you have just only one unknown theta B. So, you need one equilibrium condition here, and that equilibrium condition at theta B is MBA, means moment at B in segment BA, plus MBD, moment at B in segment BD, plus MBC, that moment at B in segment CC, that should be equal to 0. Now, there is no external moment. Had it been an external moment at B, this would not have been 0. We might have that values you need to write here. For in this case, since there is no externally applied moment at B, so total internal forces they should balance each other. Now, we know already the expression for MBA, we know already the expression for BD, and we know the expression for BC. Substitute that, get an equation and compute what is theta, what is theta B. Okay. Now, once you calculate the theta B, and then I will tell you the final values. Theta B in this case will be 1.25 by EI. Okay. 1.25 by EI, 1 point. Okay. Now, once you know theta B, substitute theta B in all these slope deflection equation to get the corresponding moments at different joints. Okay. Now, so final results I leave it to you once you know, but this is the value of theta B. Please check whether you are getting these values or not. Now, we stop here today. So, now you see what we have done here is we just applied the slope deflection concept in frame. Again we took relatively easier frame just to demonstrate the concept. Now, next class, which will be the last class of this week, we will take one more example of frame problem, but in that case the frame will undergo some sway, and we see how that sway to be considered in your analysis. Okay. Thank you. See you in the next class.